Thanks. It's great to be here. Thanks for coming. I know it's a long season of hearing talks, so hopefully this will be somewhat fun. So this joint work with my student Kent, who is no longer a student, he's at faculty at Purdue, and current student Manuel Torres, and the paper appeared in Soda 22. So you may have seen it. So this is on the densest subgraph problem, and it's a very simple and old problem, right? So it's mostly a theory audience, so the talk will be fairly focused on theory. So the problem is very simple. You're given an undirected graph. For the most part, we'll just think about unweighted, though many things extend. And we want to find some dense subgraph, right? And what is one classical notion people studied for a while is the density of a set of vertices is how many edges are there divided by the size of the set of vertices. And we want to find the densest subgraph, so we call that lambda star, right? And so here is a theory person's example as opposed to a real world network, right? Just to get the definition correct, right? If you see talks and densest subgraph, there will be usually some huge motivations. I won't do that, right? So I'll just focus on this very simple graph, right? And the clique there is has density 6 over 4, the 6 edges, 4 vertices, and that turns out to be the densest subgraph in this graph, right? So you want to find that. And so really this is one problem that among many that people study with the motivation of finding some structure in a graph which has some meaning, right? So like community detection or something interesting going on in a network, right? And there are many problems people study in that space based on objective function models and stuff. And within this space, if you just focus on this ratio problem, densest subgraph discovery, there are many variations, right? So broadly speaking, you want to find, there's some function, there's some vertex set, right? And you want to find a set which maximizes f of s over the size of s. That's the density, right? The ratio is the density. And now what is this f of s depends on how you want to model, right? Given a graph, we just look at the number of edges in the set. You can look at the number of triangles in the set, number of some patterns in that set, k-cliques, you can look at hypergraphs, you can look at various measures, right? And in fact, a very recent paper of Austin Benson, John Kleinberg, and Welt considered some slight variation, and I'm mentioning this only for some technical reason I will talk about, that you look at again a graph, and now you look at what is f of s. It is the sum over all vertices in S, the degree of the vertex in the set, raised to some pth power. Okay, if p equal to 1, you get back the densest subgraph because sum of the degrees is 2 times here. Yeah, why? It's just to see what happens maybe sometimes, right? And then also there are many constrained versions. A lot of people in this audience have worked on this densest k subgraph, right? You don't want the ratio, but you want to constrain the size of S. At most, K has been very well studied. It's a very hard problem. It's hard to prove it's very hard. Now we know a little bit more. So variations are there, right? And there are some directed graph versions and so on, right? So it's a kind of a space. One of the nice features of densest subgraph, which makes it a little bit attractive to people in practice, is it's exactly solvable in polynomial time. Right? It's one of those nice problems that can be solved exactly, and sometimes that makes it attractive, right? Even if, and also from a theory point of view, it's a nice thing, right? Why is it exactly solvable? I'll mention some, right? There's classical reduction to flow, and then you can reduce it to submodular function minimization, and then Moses Charikar gave a nice LP relaxation, which has been very influential. Samir has a nice paper I'll mention later. But one of the things that I've learned maybe 15 years ago more, right, about submodularity and supermodularity, more on submodularity, it kind of gives a nice unifying picture, and I like the topics. I've dabbled in it over the years. So one of the things that has not been, even though it's a known connection, has not been as well explored for densest subgraph is this supermodular lens that I hopefully will convey to you, right? Okay, so what is a submodular set function? Many of you know a set function over some ground set, like say vertices, is submodular if it satisfies this inequality, right? F of A plus F of B is greater than F of A intersection B plus F of A union B. There's also a definition using marginal values, right? That the marginal value of V to set A is bigger than the marginal value of V to set B as long as A is a subset of B. So this is a diminishing marginal utility property, right? And what is supermodularity? Supermodularity is a negation of that, right? Supermodular means that F of A plus F of B is less than or equal to F of A intersection B plus F of A union B. And in supermodularity, the marginal value increases as you have more. The value of an element to a set is more if you have more elements, which is the kind of the flip of submodularity. Yeah? And many times we work with submodular functions in recent years, but this is an example of a supermodular function. So let's take a graph, right? If you have this function which is on the vertices, right? The ground set is vertices, and f of s is the number of edges leaving the set of vertices S. The cut function that is submodular is a classical example of a submodular function. Okay? I won't prove it, but it's well known. But now I'm interested in f of s is the number of edges inside the set. Okay, that is supermodular. Why is it supermodular? Because you can express E of S as half of the sum of the degrees minus the edges leaving the set, right? The degrees is a modular function, right? It's just additive function, right? The degree is fixed. This is the degree in the entire graph, right? And you're subtracting a submodular function. So it is, right? So you get a supermodular function because this is fixed. This is modular, that is. And not only that, even though this is not monotone, this function is monotone. It increases. Increasing supermodular function. Yeah? Okay? All right. So now let's look at the densest subgraph in a slightly more general lens, right? I'm given an arbitrary supermodular set function, right? Because remember, E of S is supermodular. And now I want to find the densest set, right? It is clearly generalizing densest subgraph, right? And now this is polynomial time solvable, and this is good to know, right? It's a general result. Why is it polynomial time solvable? Well, okay, we want to find a set which achieves that maximum value. Well, let's look at the decision problem, which is given a value lambda, is there a set of value at least lambda? Because whenever you have ratios, you can't deal with the ratios very easily, right? It's a pain because there is right? So we would normally try to make it easier by going to the decision version. So the decision version is given a value lambda, is there a set which achieves that value lambda? Then if you do the algebra, it's asking, is there a set S such that lambda times the cardinality of S minus f of S is less than or equal to 0? Well, this is a submodular set function, now because it's a negation of S, right? And now you can check this via submodular set function minimization. It's a classical result in combinatorial optimization that given a submodular set function, you can find the minimum in polynomial time via value oracle to the function. So you can reduce this problem to submodular set function minimization. So in full general, right? And so that's why it's nice to know that any supermodular set function, that density problem can be solved in polynomial time. Of course, we want efficient algorithms, but okay. Now, of course, I mean, this is classical work. There are flow reductions and so on and so forth. Many nice results. But there's been a lot of recent attention back to the densest subgraph. One is mainly from motivation from practice for various network community detection type problems, right? Data analysis is a big thing, so there's a lot of applications, connections, so people study these problems. The other thing is, as somebody was asking, it's a classically well-solved problem. Why is it back in vogue? Maybe the data being large makes us more interested in a different class of algorithms, even though it's exactly solvable. They're too slow for big graphs, right? So you want something which is a different class of algorithms, even if it's well solved, right? And there's a lot of variations in objective, as I mentioned, right? That Austin Benson Kleinberg paper. For any p greater than or equal to 1, that is actually a supermodular function. So they observe that, but solving submodular function minimization is slow. So there's many different threads, dynamic, parallel, streaming. There's a lot of literature in the last, 10 years on this problem, right? So my focus is on this notion that even though it's solvable in exactly in polynomial time, can we get fast approximate algorithms that are interesting and nice, right? And concretely, really, this work started for me. One day I was browsing theory feed or something, and I saw that paper. Okay, yes, this random event, right? So it had some, and I don't know what drew me to it, because it was some fast algorithm. It had some nice title, flowless something, and I just glanced at it, and there was a very nice conjecture in it. Okay, and that's really what started my work, right, in this problem. Like, oh, that's a very cute conjecture. How come they didn't resolve it, right? So that's real motivation for this paper. Okay, but then I was also interested in other. There's also this connection to supermodularity and fast algorithms for mixed packing and covering, and some discrete and continuous. They're all kind of mixed together in this motivation, right? Okay, so we get a bunch of results. Let me tell you what those are at a high level, right? And hopefully you'll take away something from these high level results more than any details. So one is really this notion that it's good to keep some supermodularity connection going when I'm thinking of densest subgraph, because it's really a special case. So some results you should see it as some supermodular view, and some results are graph theoretic, right? So what is many of the results are really coming from supermodularity. That view is important. And we also answered this conjecture in that paper in some form, in an affirmative conjecture. And it was only possible to answer that conjecture because we lifted it to the supermodular setting. Even though it's a very innocuous looking conjecture, it was hard to prove it because you have to look at it slightly more general. That's one of the things. And then we also have this nice observation or a nice algorithm based on flow, which I'll mention, and which gives you a faster approximate running time from a theory point of view, even though maybe it's not I don't know how well you'll do in practice, but it's a nice connection to approximate augmenting paths, and it's a flow result, right? Okay. There are many other results. I won't mention them because it's mainly about connections, I will tell you. So what is the rest of the talk? I'll tell you about these three high-level results. With starting point was Moses Charikar's LP Relaxation, which was very nice. It's a small result in Approx in 20 years ago, right? 2000 actually. Right? But it's been highly influential, one way or the other, right? Even though in retrospect it looks very simple. And I'll also give you a slightly different interpretation of it through supermodularity, which is also nice. Okay?
Yes, all the students have also seen it as a final exam question.
Yeah. Okay, what is the classical way to solve densest subgraph is via flow or submodular function normalization, right? Then Moses came up with this nice simple LP for the problem, right? And how do you write an LP relaxation for this problem? Okay, let's look at the objective. This is just for densest subgraph, right? If you look at the objective, you want to maximize E of S by S, right? So the ratio, so it's a little bit tricky, right? But let's not worry about that. Let's think about indicator variable for a vertex, saying, is this vertex in my set or not? Right? That's the indicator. And then for every edge, you have an indicator, do I take this edge or not? Right? So, we want to find a set. So we want to pick some number of vertices, and we can pick an edge only if you take both endpoints. No? You're trying to find a set and maximize the number of edges inside the set. So you can only pick an edge if you take. So, okay. This is a natural constraint, right? XUV is less than or equal to min ZU ZV. If you don't take either ZU or ZV, you can't take the edge. And you want to maximize the number of edges you pick. Okay, now the ratio is a problem, right? So you can guess the number of vertices in some optimal solution, or because you're working with an LP, the LP will do it anyway. You may as well normalize the sum of ZV to 1. Okay, so because it's a ratio problem, you're just normalizing this to 1 as opposed to some fixed constant k. The LP will cheat anyway, so this is fine. Right? If you're writing an LP relaxation, this is a natural LP relaxation for ratio problems. In fact, sparsest cut, many of you may know sparsest cut. Exactly the same thing will happen because it's a ratio problem, you normalize something. Okay, so this is a standard way to take a ratio problem and convert it into some LP relaxation. Okay, the nice thing that Moses observed was that this is an exact relaxation for densest subgraph, which doesn't happen usually, right? It has to have some structure. So this, okay. So now the dual has some nice structure, right? Correction to flow, right? And this is usually exploited, right? And what is a dual, right? Maybe I will show you the dual via a picture. Okay. So what does the dual really say, right? The dual says, I put the dual here, but the dual looks like the following, right? The dual says, okay, I want to think of an assignment problem. So what is the assignment problem? I'm going to assign the edges on the left of the original graph, this, right, to the vertices. Okay. So think of a bipartite assignment graph, right? On the left side is the edges of the original graph. The right side is the vertices of the original graph. Okay. I want to assign each edge to one of its two endpoints. Think of it as either orientation or assignment. You can do it fractionally. I want to split each edge and assign the one unit of the edge to either its two endpoints. So you can assign 0.3 and 0.74. Right? What is my goal? I want to minimize the load on the vertices. Maximum load on any vertices. Okay, imagine I'm trying to find a dense subgraph. Now, what happens if I have a very dense subgraph? I have to assign all the edges, right? There are a lot of edges in that. I have to assign it to the vertices in that set, right? So that means the ratio will be high. Right? So the dual is saying, assign edges fractionally, one unit to vertices, so that you minimize the maximum load on any vertex. That's the dual, right? So the variables are YUVU, YUVV, right? So okay, that's the dual. Okay. Now when you see this dual, immediately a flow comes into picture, right? How will you solve assignment problems? You typically solve it by flow. So if you want to solve the dual, you can reduce it to network flow in the obvious way by guessing the maximum load. So you have to guess the maximum load. Okay. So this is actually a more natural flow relaxation than the classical LP flow relaxation. Classical flow relaxations are a bit convoluted. If you look at them, they look there's a little bit more messiness. But this is very clean. This is another way of reducing the flow. Of course, it is not immediately obvious why this is the right reduction. You have to go through some proof to show that the LP is tight, so this must be exact and so on. Okay, so now you can solve this by flow, right? But flow is slow. I mean, of course, we now have a new breakthrough, which is near linear, right? So in some sense, my result is theoretically not very interesting at this point. But still, I hope there is some value to it, which is, right? So exactly solving this flow is hard. Okay, so we can ask, can you get a quick approximate solution to solving densest subgraph, right? People have studied this from a theory point of view. So I'm going to, and then there's another motivation for studying this, right? So you can say, that one, how can you solve this LP approximately fast, right? We don't want an exact answer, but we want to solve it approximately fast. Well, the primal LP is not very good. It doesn't look as nice structure. Well, the dual LP, because it looks like a flow network, is what's called a special case of mixed packing and covering LP. Okay. So people have been studying fast approximate algorithms for this LPs for a while. There are many applications and many interesting connections. So using existing methods, you can get a 1 minus epsilon approximation to the dual in essentially near linear time, but the dependence on epsilon is 1 over epsilon square. These are based on multiplicative weight update methods. Okay. So, you can get, but, those methods tend to be slow in practice, even though they're nice theoretically, and there's been an open problem. Can you improve this dependence on epsilon square to epsilon? Right? And now there's a very nice line of work on using convex optimization techniques and accelerated gradient descent, where in some settings you can change that epsilon square to epsilon. There is well-known result of Alonso and Orecchia using accelerated gradient descent in this context. And a big open problem in this space is can you get such an algorithm for all mixed packing and covering, where you have less than equal to and greater than equal to constraints? While these results are only known for pure packing and pure covering. And densest subgraph is a case where you have both packing and covering constraints. So we didn't know how to get this one epsilon dependence. So there was actually a nice paper where people got a result where you say, okay, you can get one epsilon dependence, but you pay an extra factor, which is the degree of the graph, maximum degree of the graph. So people have been trying to get one epsilon dependence for mixed packing and covering LPs, but we don't know that yet. It's a nice open problem. But for densest subgraph, if you lose another factor of delta, you can get it. Okay, so there's a nice. Okay, so what did we get? What we show is that you can get one epsilon dependence for densest subgraph. This is not general. It's not for all LPs. For densest subgraph, you can get m polylog n over epsilon to get a 1 minus epsilon. Okay. Okay. So more. I mean, that's just the running time is good, right? It's better than what. But let me tell you a little bit of what the main interesting observation is, right? So what is the interesting observation? The interesting observation is that suppose you want to solve this this flow, right? You want to solve the flow, right? Okay, what do? You guess lambda and you try to solve max flow, right? Okay, so our main sort of technical observation is that it suffices to stop your flow algorithm when the length of the augmenting path in the residual graph is around log n over epsilon. Okay, so if you want a 1 minus epsilon approximation, either you try to solve the flow problem, right? So think of augmenting path algorithm. What do, right? You keep doing augmenting paths till you're left with no augmenting paths in the residual graph. That's how you typically solve flow, right? Okay, but that can be slow because the length of the augmenting path you have to keep going, right? So what our technical result is saying is that you start solving your flow. Once the length of the augmenting path goes over log n over epsilon, you will already be at a 1 minus epsilon approximation. Okay, I'm hiding some details, but that's so. This is sort of saying if you know about the maximum matching. Okay, you want to solve maximum matching in a bipartite graph, right? Well, you may know this Edmonds-Karp heuristic, but a nice observation is that once the augmenting path length in the residual graph is more than 1 over epsilon long, you're already at a 1 minus epsilon approximation for maximum matching. I don't know how many of you know that, but it's a nice fact to know. When the augmenting path length is long, you're already very close to optimality. Okay, it's a good thing to know, right? So you can stop the augmenting path algorithm if you only want a 1 minus epsilon approximation. So this is a corresponding thing for densest subgraph, right? It is saying once you get to log n over epsilon, you'll be good. Okay, and so that's the thing that I mean, at a heuristic level, you want to say you don't need to keep pushing flow all the way. You can stop when the augmenting paths are sufficiently long. Okay, so I won't say anything about the details, but that's a thing to take away. Yeah. So and then you also get a theoretically nice running time from some. It improves what is state of the art, but I find the structural result more interesting than just improving the running time. Yeah. Okay. So that's all I'll say about a flow-based faster algorithm. Right. That's how we prove it. Now let me move on to this what is called this peeling algorithm that Moses was motivated to analyze, right? And some new heuristic that. Okay. So although flow is very nice. People don't use if they try to use flow in very large networks, there's a lot of problems, right? Why? Because the graph itself is huge. So if you try to set up data structures for flow, you have to pay memory also. You have to pay a lot. No? In theory, we don't say, okay, another linear space is trivial. We'll think, right? But when you're working with, we are running experiments on billion edge graphs. A factor of 2 matters in the space also. Actually, many times you're space constrained than compute these days, right? They won't fit in the memory or it's just too cumbersome, right? Okay. So people use heuristics, and one of the nice heuristics that came out of Moses, Moses is, I think, motivated by this. this heuristic is a very simple greedy algorithm. Okay, what is this greedy algorithm? The greedy algorithm for densest subgraph, right, is you want to find a dense subgraph, right? So what do? You peel away the lowest degree vertex first. So this algorithm does the following. Starts and says, okay, it takes away the lowest degree vertex, puts it aside. Okay. Then it looks at the remaining graph, finds the next lowest degree vertex and puts it aside. Yeah? And so it creates an ordering of the vertices. Yeah. And then you will intuitively assume that the densest subgraph is in the suffix of it, no? Because if you're removing the low degree vertices, the densest subgraph is remaining, right? So you try all suffixes of these orderings and pick the one which has the highest density. Okay, the peeling is start with the lowest degree vertex, remove it. Next, so it gives you an ordering. Now, if you have an ordering of the vertices, you take the best suffix in terms of density. Yeah, very simple greedy algorithm. So it's so simple that people who like it try to implement it because it's very simple. And Moses showed that this is actually half approximation. And I'll mention, Samir and Varna, his student at that point, wrote a nice paper where they gave a much, a combinatorial 4-line proof actually.
Simpler than it.
Yeah, Moses analyzed it with respect, in fact, he proved it with respect to the LP relaxation, where there was a simple combinatorial argument. And then many other nice results in the paper of Samir, but I'm only mentioning that. Okay. Yeah, so in fact, I would say the fact that it's kind of interesting in science, right? The fact that Moses proved that this heuristic also has a quantitative guarantee, I think, has given more impetus for people to use it, right? Because okay, there's justification now, right? It's a good heuristic and there is a guarantee. Okay, that's great, right? So it works like that sometimes.
So is it very similar to this kind of trick of going from average degree to min degree by?
Yeah, that's it. Yeah, very simple. Nothing. Okay. So I'm just because I'm going to use it again. Here is an example to show not only that half is tight. In the worst case, it is no better than half, right? But let's see an example and also to see how the algorithm works, because I'm going to use something in building on top of it, right? So okay, suppose I give you this graph. This is the union of this graphs, right? So what is this graphs? There are some cliques, yeah. Cliques of d plus 1 vertices. Here d is 3, but in general, imagine there are cliques of size. And here is a bipartite clique, where d and big D is imbalanced bipartite clique, right? So what do you think is the densest subgraph in this example?
The big bipartite.
You can't answer because you know this problem too well. Yeah, so what is the density of the clique? Each clique has d plus 1 times d over 2, right? Over d, or d plus 1. So it's roughly d over 2, the density. Well, this one, there are only d here and a lot of vertices here, right? So everybody has roughly d, right, density. So the density of this is roughly d, while the clique is d over 2, right? So you pick this, right? But let's see what the greedy algorithm will do. Yeah, the peeling algorithm. So the peeling algorithm, okay, I'm going to break ties because otherwise the example will get a little complicated. So which one should it peel? Well, it could peel the clique vertices, but it will, because of tie breaking, it will peel this red vertices first. Yeah? Because the degree is 3, right, for everybody in the beginning. So I'm just being adversarial for the sake of example. It will peel away all these red vertices first, right? And then it will peel the clique vertices. Yeah? Okay, now your suffixes are geared towards cliques, no? While this is the best density. So if you take any suffix, either you're getting the cliques, you won't get this till you take all the cliques. Well, cliques are only d over 2 density, while this is density d. So you would basically, if you make too many cliques, this will be drowned out and your density will be the density of the cliques. You'll get d over 2 while the optimal density is roughly d. So this is a tight example to show you don't get better than half. Yeah? Okay. So that's a tight example. Now, okay, you can say, let's now, I'm going to switch my mindset. So this is fine, it's half is fine. And people have generalized this analysis to counting cliques, counting this, counting that, hypergraphs, this and that, right? Including the paper of Austin et al. They said, oh, you get 1 over p plus 1 for this strange function, right? So, I mean, because I wear this hat of submodularity often, right? I said, what happens if, is there a natural generalization of this algorithm and analysis for arbitrary supermodular function? Yeah, I mean, it's a natural question, no? I mean, what is going on? Is it a graph result or is it a supermodular result, right? And so you can say, okay, suppose I don't have a graph, but I have an arbitrary supermodular set function. The density problem is polynomial time solvable, right? And this is what is a natural extension of the greedy algorithm for arbitrary supermodular set function, and can we actually analyze it? And does it unify anything, right? And so, okay, then the algorithm is very natural. Okay. So you remove the smallest degree vertices. Now there's no degree, no? I have a supermodular function. What should you remove first? Okay. Okay. So what is the meaning of degree, right, in the abstract setting, right? The claim is you look at the vertex which has the least marginal value with respect to the remaining set. That is the definition of degree. Okay. Okay. So this is the one which is the least marginal value to the rest of the set. So v minus v is the marginal value of v to v minus v. Yeah.
Previously saying one with the smallest degree.
I can't hear very well, so I have to speak louder.
What we saying previously, we're going to grab the one with the smallest degree of those remaining. So this is now.
No,
Yes,
the
actually.
V keeps changing in every iteration too.
The v keeps changing.
I was saying from the previous.
Yeah, it's exactly the degree, right? Yeah, it's exactly the degree, right? The margin value of a vertex to the rest is precisely its degree, right? So this is the natural generalization. You remove that, then you work with the residual function, you remove it, that's it, right? So now you're asking, is there a good analysis, or what kind of approximation does this give for an arbitrary supermodular function, right? Right? Will it give half? Right? It doesn't give half. In fact, so okay. So it gives something. Okay, what is it? So we define a parameter for a function CF, and let me tell you what the CF is. Right? I hadn't encountered this before, and so we made it up because this for the analysis sake, right? And this is what it does. So what is CF for any supermodular function? I mean, it makes sense only for supermodular functions. You can define some notion of its curvature or its behavior or whatever, right? I mean, as you make the supermodular function more complex, the greedy algorithm behaves badly. It's no good if you make the supermodular function complicated. You can imagine that greedy algorithm shouldn't do so well, no? So, but you say, okay, is there some reason why it behaves well? Okay, we introduce this parameter CF for a function. What is it? So you want to compare the value of f of s to something else. What is it? Look at the sum over all the elements in the set, the marginal value of f to v s minus v. Okay, and I'll interpret it in the context of graphs soon, right? So define this, the worst case over all sets, that ratio. Okay, so let's take a very simple example. If the function is modular, what is modular means there is no supermodularity, no submodularity. F of s is simply the sum of the weights in the set. Then f of s will be sum of the weights, and this also will be the sum of the weights. It will be 1. Supermodular means that this will be growing, basically. Okay, this is supermodular means the sum of the marginal values of v to s minus v is this sum is bigger than f of s. So this number is always greater than or equal to 1 for supermodular. It can be very big. For example, f of s can be huge and the marginal values, right, f of s can be small and the marginal value can each of them be equal to that. In the worst case, this can be the size of s. But you can create a supermodular function where this is the size of s. So in the worst case, it's a very bad number, a very big number. Okay, so it depends on the supermodular. Okay, so our result, which is actually the proof is very simple. It follows Samir. I mean, you can prove it with the LP also, but you can just generalize the analysis. You get that you can show that greedy is 1 over a CF approximation for any supermodular function. And it's kind of more or less tight in many examples. Okay, so there is nothing really, the hardness is not in any analysis or something. It's just identifying that the algorithm works for any supermodular function and the behavior is given by this parameter. Okay, now let me show you what is it for a graph. Let's understand it for a graph. What do you think this is? Look at a set S. What is, if I give you a set of vertices, what is f s minus v? It's the degree of v in that set. Yeah? So the numerator is the sum of the degrees of the vertices in the set. The denominator is the number of edges in the, right? That is by definition. So what is that ratio? Sum of the degrees divided by the edge set is 2, right? So greedy gives you half approximation. Right? So really, it's the right way. This is what really greedy is doing, right? The analysis is captured by this quantity. So we're recovering all the results known in the literature, including some not so obvious ones, by just this formula. Okay, and it's not difficult to prove. I mean, if I told you prove this, you will do it in homework, right? You know, it's once I told you what it is, right? But we just wanted to look for an analysis, and this is what we found. Yeah. Okay. Okay. So I won't prove it. It's takes some time to formalize it, but I have other things to talk about, so you can look it up or try to prove it yourself and read Samir's paper on graphs and then prove it yourself. Right. It's a nice exercise. Okay.
And this is also tight.
This is tight. I mean, it is tight. I mean, we didn't prove tightness in full generality, but all the examples. Many of the examples, this parameter is tight. Yeah.
Is the CF exactly the curvature?
No. So, I mean, I think Ali is asking, some of you who play with submodular functions, there's a notion of curvature of a submodular function, how close it is to modular function, right? This is also something like that. But it's not the same as curvature. Okay, so it's a difference. See, even though submodular functions and supermodular functions are, of course, closely related in some sense, somehow this is not something I saw before. So it comes up in this problem. Why, I don't quite know, right? And I have not seen it, and this is not the same as curvature. Okay, yeah. So it's different. Yeah. Okay. Okay. So I mean, as far as I know, it unifies all the known results in a simple way, and so that's the value. Okay, now let me come to the problem that really started me thinking about this. This is iterative peeling. Okay? So this is done by this big group at Georgia Tech, right? And they realized that, okay, peeling is great. It's a simple algorithm, right? It's very easy to implement, but its approximation ratio is not great, no? It's half. Okay, it works very well in practice, but in many cases, but it's still, while we can solve it exactly, we're settling for approximation because it's a big problem on a big graph, so it's okay, but it'd be nice if you can come up with a heuristic which is, gets closer to optimality while still being simple. Yeah, I mean, I think that's a thing that maybe in theory we do less of, but we should do more of, right? But so they realize, of course, that there are all this packing LP formulations like I mentioned, but they're kind of complicated, or they wanted something very simple, and they came up with this heuristic, okay, which is an adaptation of peeling algorithm, right, based on some intuition they had from the dual LP multiplicative updates, and their goal was to change this half to 1 minus epsilon, but in a simple algorithm. So okay, so they call it iterative peeling. So it does it many times in some adaptive way, right? And then they claim that it will converge to some solution. So what is an algorithm? The algorithm is a variation of this peeling, right? In the first iteration, it does this greedy algorithm. In the next iteration, it does something a little different. Okay. How does it do something different? It maintains some notion of a load on a vertex. Okay. Initially, all the loads are 0. Okay. All the vertices have no load, right? Because you've done nothing. And the first iteration is a greedy algorithm. Okay, so after you do the greedy algorithm, I mean, it comes from the dual, I'll interpret it later. You assign to each vertex a load, which is all the edges that you were incident to that vertex when you peeled it. Okay. So let's look at the greedy algorithm. First vertex, what do? You remove the vertex with the lowest degree. So you assign all those edges to that. That becomes its load. The next vertex, when you peel it, there are still edges incident to it, right? That becomes its load. Okay. So at the end of the first iteration, you get a load vector which is non-zero because you assign those edges. Right? So in the second iteration, you don't peel based on the degree, but you peel based on load plus degree. Okay, I'll give you an example. Okay, now in the second iteration, you update the load by again assigning all the edges you incident to the vertex when it is peeled to that vertex. So the loads keep increasing. Okay, let me give you an example.
So I think you go back to the factor 2 tight example.
Yeah, I'm going to do this. Okay, that's okay. Let's do this. Okay, remember initially loads are 0, no? So what did we create? We created this ordering, right? Okay, but when we created this ordering, when I peel this red vertex, what happens? All these 3 edges are assigned to it. So its load is 3, right? This is 3, this is 3. All of them get 3 except at the little bit noisy at the end, right? But what about these guys? They get 2, 1, 0. Don't worry too much about this because they're at the end. You have to be a little careful, yeah? But the thing to remember is all of these get load of 3 roughly. Okay, what happens to the clique? When we peel the clique, the first vertex in the clique gets load of 3, right? Yeah? The second vertex gets 2, right? Because by the time this is removed, there's only 2 edges incident. So it gets 2, 1, 0. Yeah? Makes sense? Okay, in the second iteration, what are we doing? We are picking the vertex with the load plus degree, which is smallest. Oh, which one is that?
The purple one.
Yeah, this one, right? Yeah? Okay. And then what happens? All these zeros get picked, right? Okay. So the second iteration, all the clique vertices get picked first. Yeah? Okay. And then, this is load plus this is basically 6, right? You won't pick this till you're done with all the cliques. Now you're golden, right? This in the second iteration itself, this algorithm is going to find the optimal solution. In this example, I'm not saying it should. Is that okay? Make sense? Is the algorithm clear? Okay, now, I mean, it keeps going, in this case it stopped, but it keep doing it for some number of iterations, right?
So how did you choose capital T?
Okay. That's okay. At each iteration, it creates an ordering, takes a suffix, keeps track of the best one it has seen, and at the end of T iteration, it outputs the best. That's a very natural thing. Their conjecture is this. They conjectured that after 1 over epsilon square iterations, it will give you 1 minus epsilon. Okay, so T equal to 1 over epsilon square means 1 minus epsilon.
So every time does it improve?
No, it doesn't. No guarantee. So they couldn't prove anything in terms of the formal guarantee. They came up with this beautiful algorithm because it's beautiful in the sense it's so simple. And it says motivation. There is some motivation. But this is a conjecture. Okay?
Sorry, I'm a little confused. So there is, in the original greedy algorithm, you keep removing minimum degree vertices.
Adaptively, right?
Adaptively. And then you stop at some point, right?
You don't stop.
So you look at the worst one or the best one, and then that's the
output.
That's the output. Right? So here, are you doing it in phases of?
No, you create the first ordering.
Okay, you create the whole
first ordering, you create a whole thing. And then the loads you get a new load vector, right? Okay. Now in the second iteration, you're peeling based on, imagine the initial load was 0. Okay. Load plus degree is simply the load, the degree, at that point. Okay. The second iteration, you already have loads which are non-zero, which are based on the first iteration. Okay. And then your second iteration peeling is simply load plus degree. The degree is changing, but load doesn't change in that whole iteration. Right?
Okay, so I see. I had somehow thought of it as actually deleting vertices.
No. You redo the whole graph. Okay?
How do you get the load for the third iteration? Is that just the degree when you peel it away in the second iteration? Or is it the load plus degree when you peel it away?
No, load plus degree. Right. That is why you see, in the second iteration, what is the load plus degree of this vertex? 6. The load plus degree is 3 for this.
Yeah.
So you peel that first.
But
What's
maybe
the
have
load
question
of
what
the-
will happen in the next iteration.
Oh, next iteration, the load of this vertex becomes now it was 0, right? Now it becomes 3. See, whenever the update to the load is whenever you remove a vertex,
You add that.
you add the edges incident at that point to the load.
But you don't take away what was already in the load.
No, loads keep increasing.
Yeah, actually related to this question. So what happens if we just look at the previous nodes and not aggregate all the nodes that they have since?
I don't know. This is their algorithm. Okay. Yeah, but this is their algorithm. Yeah. I don't know.
There is an example that works. I don't know.
Yeah, I don't know. I haven't thought about variations of the algorithm. This is their algorithm. Yeah. So I think you had a question here.
I guess in the worst case example, you can have a bunch of vertices that have the same degree, and that really depend on your tie breaking or like the way that you choose the one vertex. And I guess maybe adding load into consideration is kind of combating that random choosing, because then.
No. That's not the reason. It's not tie breaking. That's called. I chose this example for tie breaking because otherwise it's a pain to create big examples. You can that tie breaking is not the reason. You can make it slightly bigger. So the intuition is not coming from tie breaking. There's something the loads are doing, which and that load should imagine the dual doing the loads and stuff, right? So
Yeah, if you make the pleats just one bigger.
yeah, one bigger.
Yeah,
I couldn't draw it right, and so tie breaking is not the intuition. Okay, they made this very nice conjecture, right? I'll make sure I have time. Yeah, okay. Okay, and this very strong conjecture, no, very nice conjecture, right? Small number of iterations, you'll get very close to optimal. They couldn't prove that it is actually better than half.
Oh, nothing better than.
How did they guess 1 over epsilon squared then? Like, why did they pick that number?
That's because it's coming from this multiplicative weight update intuition. Okay, there's intuition behind what all the things they did, but okay. This, and they ran experiments extremely good. I've run it too. I have it on my laptop. Right? You run it on, huge graphs, and they optimized also the implementation. It's like super fast, super good. And I don't. Okay, so what did we do? Okay, so what I wanted to understand was that, in fact, just like we generalize this greedy to supermodular functions, you can generalize this also to supermodular functions. This iterative version. And it is very important that we did this. Why? Because it's only through this generalization we could see the proof. Proof, not the grade, right? Okay. All right? Okay. So I won't describe it as a mistake. I mean, the algorithm is the most natural. You maintain loads and stuff. Okay, so what did we prove? We proved that this iterative peeling algorithm not only works for densest subgraph, it works for all supermodular functions. But we didn't prove exactly what their conjecture. Right? What did we prove? We proved that this algorithm converges to 1 minus epsilon approximation in 1 over epsilon square times some other parameters, right? Which depend on the function. And that is log n, okay? And max f of v divided by lambda star. Okay, forget about that supermodular thing. If you look at it, densest subgraph, we are proving it converges in 1 over epsilon square times the maximum degree over lambda star times log n. Okay, this factor is not
term there.
Sorry.
There's still a log n term there.
Yeah, that is still not right. Small. Maximum degree can be huge, and so it's not a small term. But the lesson is that it converges. Okay, and that, I mean, it is a good algorithm is in some ways that it at least we can prove it converges. It's not like the quantitative dependency is the reason they couldn't prove. They couldn't prove that converges at all. Right? So okay. So why could So that's the main result, right? And so how did we prove it? I think that's maybe more also interesting, right? The thing which is, I think, caused trouble, right, in trying to find a proof, is that you can see, right, the algorithm is working with orderings, no? So while the LP relaxation, right, if you remember the dual, it's like assigning edges to this. So that's where intuition came from, the loads and. Right. But so how do you understand these orderings as first class objects, while somehow you're working in the dual with loads and assignment, right? So in some sense, when you go to supermodular set functions, orderings become first class objects. Okay, if you know polymetroid theory and supermodular functions, submodular functions, the ordering becomes first class object. Okay, then it's more transparent what's going on. And so you also get a more general result, and also you see why the ordering comes in action. Okay, so it's still technical. So what we did is that we showed that the Moses LP relaxation is a special case of a relaxation for any supermodular set function. And then we rewrote that, it's essentially a convex program, into a linear program. And we showed that the iterations of this greedy plus algorithm are approximately implementing some multiplicative weight update algorithm on that LP. Okay. So it's kind of a roundabout proof to understand this algorithm. Okay. It's not a perfect answer because we don't know lower bounds on the performance of this algorithm other than 1 over epsilon. I'll mention that at the end. Okay. So one thing I want to tell you is that, let me go back to, some of this is technical, but I just want to give a flavor of some ideas. So if you're interested, let's look back at Moses LP. Yeah. So what does Moses LP say, right? It has maximized sum of XUV subject to ZV equals to 1 and XUV is less than or equal to min ZUZ. Okay. I'm going to rewrite this as a slightly different LP where I don't want this variable's XUV. Yeah, I don't want XUV. Why? Because when I go to a general supermodular function, I have no edges, right? They're just variables. Okay, but let's remove that and let's write this. Look at that. Yeah, but this is the same LP, no? Except it's not an LP anymore because I have this min ZU ZV term sitting in the objective function. It's not linear, but it's actually concave. Okay, so that's nice. So is there a meaning to that, right? Is it some just random coincidence or is it just meaning to it? Well, it's not a random coincidence. Actually, you can prove that it is it's just what is called a Lovász extension based relaxation of a supermodular set function. Okay, so there is a natural way to take any supermodular set function or a submodular set function and extend it to the continuous domain. Okay, and there's something classically well known called the Lovász extension. It's a way to take the set function and make it work in the continuous space. Okay, and for there are not one set function, there are multiple ways of extending a set function to continuous spaces. In the context of minimization, Lovász extension is the one to use. It turns out that Moses LP can be generalized in the most natural way if you want to solve maximum supermodular densest subgraph using this relaxation. And it is exactly the generalization of law, and it's exact for supermodular set function. Okay, it's a long ago simple observation that we made, and then you have to do some transformations. I will not have time. It's a lot of technical stuff, which is, if you know the machinery, it is not unnatural. It's just that, from you take some duals, you do some manipulation, you can rewrite the same problem, LP relaxation, in a different LP relaxation. Right? So this is the LP relaxation. I won't explain it too much to you, but it is written with an exponential number of variables and a polynomial number of constraints, where each variable corresponds to an ordering of the ground set. Okay, the only thing I want to take away is that, remember, this greedy algorithm is creating many orderings along the way. It's hard to understand those orderings without orderings being a first-class object, right? And this LP, even in the supermodular setting, is expressing that relaxation in a different way where the objects are actually orderings. Okay, you're packing orderings according to some rule, right? And okay, so then once you have this, you can come up with an algorithm which is just plain multiplicative weight update algorithm based on this LP relaxation. And that gives you actually an algorithm for solving densest subgraph supermodular set problem in some polynomial 1 minus epsilon approximation. Except that we wanted to prove that this greedy plus algorithm is implementing that multiplicative weight updates. But it's not quite implementing this multiplicative weight updates because of this degree correction. But we can prove that it approximately implements the multiplicative weight updates algorithm. That's good enough. So it's not quite a clean answer, right? The proof is not as clean as just mapping it. It still involves some manipulation to show that it is approximately implementing the multiplicative weight update. Okay? So as a corollary, we get the fact that it converges in this number of iterations. Right? Okay? But it's not the final answer. Why is it not the final answer? Well, I think I'm running out of time, so I'll just go to the open problems as a segue from this thing, right? Well, we showed it converges, right? And supermodular perspective is important, but we don't know the tight analysis for this algorithm. Okay, the best, not that word. You got to use the word best or worst, right? The lower bound on the number of iterations it requires to get to 1 minus epsilon, we can prove is only 1 over epsilon. We know it takes 1 over epsilon. It has to take 1 over epsilon iterations in some cases. But so we don't know that their conjecture is right also. Whether it is 1 over epsilon square or 1 over epsilon, we don't know. Even constructing this example would be interesting. To prove that it takes 1 over epsilon square iterations is not at all trivial. We spend some time, right? Okay. And also remember, we have all these extra terms. And their conjecture says there's no extra terms. It's only 1 over epsilon square. So removing any of those terms is also interesting. Right? So we don't have a tight analysis of that algorithm. We only know that it converges by relating it to some other algorithm. Okay? But one nice thing we got out of that is that it converges for any supermodular set function. So it's not really a property about graphs, but really a property about this greedy algorithm for supermodular set. Okay, and that's all I want to tell you. Yeah. So you have some new heuristic variations based on some other things which seem to do even faster than this heuristic. So that seems, even though the theory says it takes longer time, heuristically it's doing much better than even this heuristic. So there are some things we are exploring, but the main theoretical conjecture is still open about this particular algorithm. It seems very nice, right? Simple algorithm. That's it. Thank you.
So I know it's 1 o'clock. Those who need to leave can leave. Leave you around for the next 10 minutes to answer questions. But thank you so much. I've been sitting in this room for 3.5 months listening to talks on machine learning, AI, NLP, quantum computing, cryptography, and the percentage of material I could absorb kept going down. So I was thinking maybe it's time for me to retire. But today you sort of gave me another 5-year lease in life because I understood almost every word you said. So thank you.
Yeah, I think you were very close to this line of work, and yeah, I mean, I didn't pay attention to Moses' LP and your thing that much because I didn't work on it, right?
Yeah,
so it was very nice for me to go back and find all these nice connections to this previous paper, some hardness results, some even like generalizing it to supermodular functions as parameter was very pleasing to me because as you get older, you want simplification, not the complexity of proof or right something that you can explain in a short. Okay, you don't have to remember a lot, right? This is a clean way of remembering the analysis and explains many things. That's more satisfying than I wrote 10-page proof or something that many people don't read, right? Hopefully, this will be useful, right? That was nice for me. Yeah, anyway, so it's an advertisement also to learn to some extent some of the classical results on combinatorial optimization. I just finished teaching a class on combinatorial optimization, right? On supermodular functions, submodular functions. I mean, just like in math, right? Use abstraction. Even in theory, we have all this nice combinatorial optimization machinery, which is not maybe as well studied in CS. But it's very beautiful and it's very powerful when you read it. So,
all right, thank you so much.